Hey, this is Jeffrey and Victor, back again with another Webots Erebus tutorial. This is tutorial number 3, and in this video we're going to teach you how to use the sensors of Webots. So by the end of today, you should have code in either C++ or Python, depending on which language you're going to use. You're going to have code to probe all the sensors that you might need for the Erebus R competition. And just like the last video, our main segment is going to be in C++, and then we'll have a section at the end in Python that gives all the Python equivalents of the C++ syntax. So if you're using Python, just look there and that'll give you all the syntax that you'll need. However, you should still watch the C++ section because in that section we're going to go over all the important concepts of using these sensors. So in Webots, we can take a robot, such as this one right here, and we can add sensors to it. Now, the people who created the Erebus world have already added these sensors onto the robot for you. So you don't have to add or take away any sensors from this robot, and nor should you. So to get a list of all these sensors on this robot, we can go over to the scene tree, and we know that this is robot 1 because when I click on it, it lights up as robot 1. I bring this down, and we can go to extension slot, and this is where all the sensors will be added. So if I bring this down again, you'll see a list of all the sensors attached to the robot. There's a gyro sensor, receiver, emitter, light sensor, GPS, and camera on the robot. In this video, we're going to go through each one of these sensors individually. One thing to make note of is you'll see that for each sensor, you have one word followed by another word in quotation marks. The first word is the type of sensor it is. So this is a gyro sensor, this is a receiver, this is an emitter, and etc. This name in quotes right here is the name of the sensor itself. So this sensor's name is gyro, this sensor's name is receiver, and etc. So you'll see that they're all the same as their type, but if they were different, remember that this is the name of the sensor, and that's going to be important in the next part. So here I have the basic sample code for one robot and a sensor attached to that robot. Now, for any sensor that you use inside of Webots, there are 4 basic lines of code that you need to make it work. The first line of code is your pound include statement. This grabs all the gyro functions that you might need and it brings them so you can use it inside your robot controller. Now you might be wondering, how do I know that this is called gyro.hpp? Good question. Well, I got this from the type of sensor that I need. If you remember in the last segment, we talked about inside of the scene tree, I go to robot 1, extension slot, I can see a list of all the sensors on the robot. If I want to use a gyro, the header file that I need is just uppercase G gyro.hpp. So I just use the word on the left-hand side and I add .hpp to the end. And that's how I get this include line. So let's say I wanted to use camera instead. Over here, I have the type of sensor is the camera because that's on the left-hand side. So I use camera, uppercase C, .hpp, and then this would just become camera.hpp with an uppercase C because the word on the left-hand side has an uppercase C. But let's stick to gyro for now. The next line that you need is an object. So I need to create my gyro object. I can then use my gyro object to call gyro-related functions that we'll see later on. To do that, all you have to do is create gyro. Once again, this derives from the type of sensor that it is. So uppercase G gyro right here. This is a pointer. And then this is the name of my object. You can name it whatever you want, but we suggest sticking to something simple like gyro or my gyro. Then I just do robot arrow get gyro. Now each sensor has its own individual get method, and I know this is get gyro because if I go to the documentation, which I'll show you how to get to in a second, I can scroll down to robot, click on it, and then I can scroll way down till I find the get methods. And if I go to C++ and I look for the one that I want, which is the gyro, I can find get gyro. And you can see there's a list of all the sensors you could possibly need. So GPS is get GPS, get camera is get camera, and etc. For the most part, it's just the lowercase g get followed by the type of sensor that it is. Then inside of here, I don't pass the type of sensor it is, but I pass the name of the sensor. So you'll see that inside the scene tree, to the left-hand side, we have the type of sensor it is. Then to the right-hand side, we have the name of the sensor. So inside of these parentheses right here, I pass the name of the sensor. In the other instances, like over here and over here, we use the type of sensor, as you'll see by the uppercase G gyro. But then inside of here, we pass in the name of the sensor, which is in quotation marks and lowercase g. So that's 2 lines of code. The next line of code we need is the enable. This basically just starts up your gyro. It's like calibration. Then inside of here, you have to pass your time step. You can get your time step by calling time step equals robot get basic time step. And time step right here. Remember, the time step is just how often this loop is iterated, and I need to pass this variable into this enable function. Now that my gyro is enabled, I can get its values with the getValues function. Now every sensor has a getValues function, but what it returns is a little bit different depending on the sensor. For example, my gyro getValues returns an array of 3 elements. We'll explain what that means in more detail a little bit later. So basically all I'm doing right here is I take the array and I index the first element. So in review, every sensor that you use needs a pound include, where you pass the type of sensor.hpp. It needs a constructor line where you construct an object, so you can use that object to call sensor related functions. Then you have to do an enable where you pass in time step. Then you can just do a get values using your sensor object. So this is the syntax for the basic lines of code you need for any sensor. Now, for each sensor, it's going to work a little bit differently, and that's why this is just the basic overall idea, and we're going to go specifically into each sensor later on in this video. So one of the most important parts of robotics is reading documentation. And on their website, Webots has a lot of documentation on all the possible sensors, motors, or whatnot that you might need inside of the Webots world. So to get here, all we do is Google Webots. We click on their website. We go to documentation, and we go to reference manual. Then from here, we go to nodes and API functions. So this right here is very important. We'll put the link to this inside the description of this video. But here, you can read the documentation to any sensor or device you may need. So for example, let's say we want to read a little bit about our ultrasonic sensor. So that's going to be called a distance sensor. So I just scroll down, I can click on distance sensor. Then you can see how the distance sensor works, and you can see all the functions down here. So these are all the functions that you might need when using a distance sensor, and it has C, C++, and Python. And additionally, since the ultrasonic sensor works a little bit weird as opposed to your normal ultrasonic sensor that you use in real life, you can read all about that over here. And they have a nice graph to show you how the ultrasonic sensor exactly works. So if you're ever in doubt or you need help using a sensor, Your first resort is to come over here and read the documentation and look at any functions that might help you out or any of this information that might clear up any issues that you're having.
We last left off with the box challenge where we used the gyro sensor in order to give a precise angle heading of the robot so we could make 90-degree turns to have the robot go in a box. So since this video is all about the sensors on the virtual robot, I'm going to reiterate what was said about the gyro in this video as well, because we just want one entire video dedicated to all of the sensors. So here I've created a new controller called Sensor Sample, and I'm going to use this controller to demonstrate all the features of the virtual sensors. So you might recognize this from the last video as well, from lines 14 to 20. All I'm doing here, if you remember, is creating the sensors. And specifically on line 16, I'm creating the gyro. So if you remember, all we have to do is say gyro, asterisk gyro equals robot get gyro. And then in the string, we have the name of the sensor, which is, in this case, just gyro. So what's important to note is that Webots' gyroscopes function like real-life gyroscopes. It's not like you might have used NXT or EV3 gyros where they give an angle heading in degrees. These gyros actually give you the angular velocity, and we've said this in the last video. We're just going to say it again. Here we have a function called update gyro, and it takes in a time step of the world. So usually this is around 32 milliseconds or some multiple of that. And in this case, all we're doing in this function is we're integrating the gyro's angular velocity in order to actually get an angle heading that we can use. So what we're doing is we're converting the time step, which is in milliseconds, back into seconds. And then we're multiplying that by gyro's get value. And you'll notice that we have a bracket 1. And the reason why we have that is the gyro actually gives you the angular velocity on 3 axes, the x, y, and z axes. But since we only care about the robot's yaw, we're actually only getting the rotation around the y-axis, which in this case is the first index because it functions so like it's x followed by y followed by z. So with a bracket 1, all we care about is getting the rotation around the y-axis. Now, if you wanted to get the rotation around the x-axis or the z-axis, then you could do 0 or 2 respectively. And this actually functions, you can index it like an array, because for those of you who use C++, this just returns a pointer. So like we've said before, the best place to actually find information about a particular sensor in Webots is to visit Webots' reference manual online. So right here, you can just go to cyberbotics.com and they have their reference manual. So here's a description of all of the sensors as well as everything else within Webots. And here's the gyro. And over here, you can see what the gyro actually offers you. So like we said before, it tells you the rotation around the X, Y, and Z axes, as well as how to enable, disable the functions associated with it, including get sample period, and what we're really concerned about is getting the values of the actual gyro. So once again, the gyro only returns the angular velocity. So I'm going to demonstrate that right now, and all I'm going to do here is actually print out the angular velocity of the yaw. And remember, all you have to do to use the gyro is, first of all, you have to declare your gyro sensor. Second of all, you have to enable it with your time step. And from then on, you can get values from the gyro. So right here, all I'm doing is printing out the angular velocity revolving around the y-axis. So I'm going to build this program. I'm going to run it. And right now in the console, you can see that the gyro is saying that we have an angular velocity of 0, which means that we're not turning in like either direction. If we move it around, and fun fact, you can actually apply forces on objects in Webots within the simulation by holding Alt and then right-clicking on the object and dragging it around. So like so. And the gyro goes out of control because we just flipped the robot over by applying a force. So there you can see that it's not actually representative of the angle heading, but the angular velocity, because although our angle heading has changed significantly, the current angular velocity is still 0, which means it's not turning currently in either direction. So I'm going to pause and reset that. Okay, so next we'll be talking about the ultrasonic distance sensors that are on the Pioneer 3DX. And the Pioneer 3DX actually has 16 ultrasonic sensors, and how we know that is because, once again, if you look at the Webots reference manual, they have a page for every single virtual robot that they supply as a proto. So for instance, this is the Pioneer 3DX page on the Cyberbotics wiki. And if we scroll down, you'll notice this image right here gives you all of the ultrasonic sensor positions. And if you count, there are 0 through 15, so that's a total of 16 sensors. And they go from back to front. And on this image right here, you can actually highlight the different ultrasonic sensors that are on the robot. Okay, so in my sensor sample code, the way I'm going to be accessing these ultrasonic sensors, and we recommend using the same way, is we're not going to assign each ultrasonic sensor its own name. We're going to have an array of ultrasonic sensors instead. So in this case, the ultrasonic sensors are just called distance sensors. And this distance sensor class includes not only ultrasonic sensors, but a variety of other kinds of distance sensors, like infrared sensors. So this applies to whatever kind of distance sensor you're using. And in this case, we're going to create an array of 8 ultrasonic sensors. So we're actually going to use the frontal 8 ultrasonic sensors. And the way they're arranged is that each ultrasonic sensor points at an angle surrounding the robot. So once again, bringing this back up, they're pointed so that these they sweep from the sides all the way to the front of the robot. So you essentially have 360 degrees of vision of detecting distance. All right, and since we're only using the frontal 8, that includes sensors between 0 through 7. So we create an array over here of 8 ultrasonic sensors, and the way we enable all of them is we actually have in our main loop a for loop that iterates through 8 times, and all we do is simply index each sensor from 0 through 8, or 0 through 7 actually, and we get the name of the robot's distance sensor by doing SO, which prefixes all of the distance sensors, as well as concatenating a string of the index of the sensor. So that's either 0, 1, 2, 3, 4, 5, 6, 7. And then we enable that sensor. So this actually sets up all 8 of the frontal sensors. If you wanted to use 16, then you just use an array of 16 distance sensors, and then you have a for loop that iterates through all 16 sensors. But since we're only doing the frontal 8, this is what you need to do. All right, so if we want to print out the value of a distance sensor, all we have to do is, like down here, you index the distance sensor that you want to get the distance of, and then you just say get value, like all the other sensors we've seen before. And this returns a value not in the actual distance from the sensor to an object. If you've ever used NXT or EV3 distance sensors or ultrasonics or infrareds, they return a distance, I think in centimeters. Webots treats this a bit differently. They actually give you a value between 0 and 1024. So this is the Webots reference manual, once again, for the distance sensor. And at this point, you might be wondering, if this is a simulation, how does it simulate noise in real life? Because we know that sensors in real life don't have perfect accuracy, right? They always have some sort of noise associated with them and a degree of accuracy. So how Webots actually simulates this is with something called a lookup table. And if I scroll down, they have an example of a lookup table. So the x-axis here is distance to the wall, and the y-axis is the measured value that the sensor returns. So what this lookup table does is it associates the distance, the actual simulated distance from the wall, versus what the sensor value is going to give back. And you can see here that Webots actually allows you to add noise, or however much noise you want, to the sensor reading. You could have a perfect sensor which has no noise, but in this case, that's not necessarily going to be the case. You can add however much noise you want to your sensor depending on what you're trying to simulate. So since our sensor goes from 0 to 124, that's not in meters or centimeters or any unit of distance. It's just the value that the sensor has. So in order to find out actually how far away from the wall is what's distance, you're going to have to measure that within the simulation and just print it out and see for yourself. So let's do that very quickly. I have a line printing SO4, and this is the 5th distance sensor in the front, which is approximately directly in front of the robot. So if we build this, and then run the simulation, it's printing the current value of SO4. And the distance from an object and the sensor return value is actually inverted. So 0 means that it doesn't see anything at all. But if I move this robot towards a wall, you can see that it's starting to increase. And if I move it really close to the wall, it reaches around 1,000. So the further you get from the wall, the lower your sensor reading is going to be. And the closer you get, the higher it's going to be, up to around 123 or 1023. So the virtual robot also has a GPS sensor that allows you to get the absolute position of the robot in the world. We set it up like any other sensor we've done already, which is just saying we get robot get GPS, and the name of the sensor is just GPS. And we enable it down here. So how the GPS works is that it returns you the X, Y, and Z position relative to a point in the simulation. In this case, you can actually find what the point is relative to in the world info. And right here, there's something for GPS reference, which is just the origin of the world. So in this case, our position of the robot is going to be relative to 0, 0, 0. Where that is actually right there. So this robot is not actually at the world's origin. So its position, as you can see, is very different. If we were to run this program and just print out the GPS's values, then we would see that our GPS values are the same as the transform that's listed inside of the scene tree. So right over here, all I'm doing is printing out the GPS X position and the GPS Z position. the GPS Y position is the height of the robot within the world, so we are not actually concerned with that. Let me put a space there. And once again, like the gyro, this follows X, Y, and Z again. So we're indexing the first value, which is X, and we're indexing the third value, which is Z. So that's index 0 and index 2, respectively. So if we build this, and we run the program, you can see that it's printing out the X and Z coordinates. And if we look at the transform of the robot given in the scene tree, it's the same as what's printed in the console right now. So if we were to move our robots around the point of the origin of the world, which is right there, so if I move the robot there, it gets pretty close to 0, 0. Obviously, I'm not perfect in that case, but you can see how it's relative to the center point of the world. And since this whole maze is built around the center point and it's centered around 0, 0, 0, then the center of the maze would be the center point of the world. Finally, we're going to talk about the camera. So we're actually going to go in depth more with camera recognition of game objects in the next tutorial, but we thought we'd give a brief overview of what the camera can do. So in Erebus, the purpose of the camera is, of course, to recognize victims as well as activity zones within the game. And Erebus actually makes this really simple because objects within the game can have these things called colors. And this does not refer to the actual color of an object. Like, for instance, the ground is white or the walls are gray, but each object can have a color object associated with it. And what I mean by that is, for instance, if I were to run the simulation, and if we select a game object, like for instance, this cube, you'll notice that it actually has this field called recognition colors. So attached to this object is a color object, and you'll notice that it's just an RGB value. In this case, red, green, blue, and red and green are set to 1. And we know that red plus green makes yellow. So that's why this this object is colored yellow, but its recognition color object is also itself yellow. So we can actually use the camera to automatically detect any object that has a recognition color field associated with it, as long as color recognition is enabled for that object. So for instance, if I were to run this code, all we do is say we print cam get recognition number of objects. And this prints out the number of objects that the camera currently sees in its frame. And you'll notice up here that this screen, once we enable the camera, is actually, it actually displays something now. And in the perspective of the robot, the camera is facing forward, so it actually sees this open doorway right here. And the other image is still black because this is actually the camera for the other robot. So this is the camera view for robot 1, while this is the camera view for robot 0. And since we haven't enabled the camera on robot 0, then it remains black. Only when you enable the camera does it actually show anything. You'll notice that the picture is very pixelated. Webots actually lets you set whatever camera settings you want, and we specifically reduced the resolution of the camera because it speeds up the speed of the simulation. Okay, so I wrote some more code over here, and one thing I actually forgot to mention was that in order to use the camera recognition features, you actually have to enable camera recognition by doing cam recognition enable, and then pass your time step in. So all I'm doing once again in this program is printing out the number of objects the camera currently sees. So if I build this and then I run the program, you can see that it says that we see 7 objects in the camera view. And if you'll notice, these red lines actually start popping up, and these actually demonstrate what the camera is recognizing. These walls actually have a color associated with them, so the camera can actually recognize these walls as well as the victims and the activity blocks. So right now it says that we recognize 7 objects, and if we move this robot in front of, say, this block, you'll notice that it draws a red box around the block. And we currently have 1 object that is being recognized. Okay, so now what I'll do is actually once you recognize an object, Webots makes it really easy to extract information from that object. So if I pull up the documentation page for this, for the camera recognition object, it passes back, allows you to access multiple values from the object itself. For instance, you can access the object's position, orientation, size, as well as the position on the image and size on the image. And the position and orientation is actually relative to the camera itself. It's not relative to the world's absolute positioning system, like the GPS is, it's relative to where the camera is. So for instance, I have additional lines of code down here, and all it does is it checks, first of all, with an if statement, if the number of objects the camera currently sees is above 0, so there's at least 1, then I simply print the position of the first object it sees. And in this case, I'm printing the X and Z positions. I'm not printing the Y position because once again, the Y position is the height and we don't really care about the height. So I'm printing only the X and the Z. I'm going to reset the world, build this program, and then let's see if we can get the position of an object. All right, so let's say I move my robot in front of this yellow object right here. And you can see that it currently says we're pretty close to the object. If we move in even closer, then it gets very low, and then eventually we pick up the yellow object. So we're going to go in depth into victim retrieval in the next video. But for right now, you can see that once we got really close to the object, this position started decreasing. So this is very useful for not only finding objects, but directing your robot to go towards the object and eventually collecting it. Finally, for the more advanced users, Webots camera images can actually be used with libraries like OpenCV to perform advanced image processing. This most likely will not be mandatory for the actual Erebus competition. However, for those interested, Webots has a sample world demonstrating this functionality. So if I go to File, Open Sample World, Samples, How To, and then Vision, if I open that world, this is just a demo world that Webots uses to demonstrate how to use OpenCV in your projects. So just a brief overview of what this program actually does is that you get the camera image just like how you would a regular camera like we used. And note, however, this is the C version of this code. After we get the camera image, we use OpenCV to construct a mat of that image. And the image data is actually in RGBA, so we can just easily convert that into a mat. And then afterwards, all this does is convert it into HSV. So for those interested, you can look more into using OpenCV with Webots projects. But for camera recognition, it's perfectly fine to just use the color objects associated with the actual game objects within Erebus. One final note is that you may have noticed some other sensors attached to the robot that we did not go over. So under extension slot, we covered the gyro, GPS, and camera, but we didn't go over the receiver, emitter, and light sensor. So first, let me talk about the receiver and emitter. This is not necessary for the competition. This is more used to communicate between other robots that also have receiver and emitters. Since this is an individual robot competition, we don't actually use the receiver and emitter ourselves. Similarly, the light sensor is another sensor that we probably wouldn't have any application for as of right now, at least. This light sensor measures the light from a game or a simulated light source. So these light sources include point lights, as well as in the description it says spotlights and directional lights. They don't, however, allow you to tell the light reflected off of an object.
So sensors in Python are very similar to sensors in C++. They have the same basic 4 lines of code that you need. So for the most part, I'll let you use the documentation and figure out the functions for yourself. But I'll guide you through a little bit of it. So just like the C++ version, you need your header. So we're going to do from controller, import light sensor. And as before with C++, light sensor, this is derived from the type of sensor that you're using. So in this case, I'm using a light sensor as an example. Remember that light sensors are pretty useless to you for this particular competition. But this robot has a light sensor, and I can tell its type by the word on the left, which is uppercase L, uppercase S, light sensor. So that's what I'm going to plug into here for my import statement. Then I'm going to grab a light sensor. So I know this method name is getLightSensor because if I go to my documentation and I go to the robot part, then I scroll down, way down, I can find all the getSensor functions or getSensor methods right over here. And you will see that getLightSensor is right here for Python getLightSensor. There we go. And then it has one parameter for its name. And just like the C++ version, I'm passing the name, not the type. And the differentiation is this word on the left is the type, and this word on the right is the name. So inside of here, I'm going to be using the name of the sensor, not the type. So I can create my light sensor object. I named it ls. So I can now use ls to call light sensor functions. For example, just like in C++, I can do ls.enable, then I pass it my time step, all the same. Then I can also do ls.getValue as you can with any sensor, and then I can just print that out. So this will print this out continuously. And you can read about your sensor's getValue function or getValue method inside the documentation. If I find light sensor, then I go to getValue, I can see right here. Then getValue function returns the most recent value measured, and etc. So just like in C++, in Python, you need your import statement, where this is the type of sensor. You need to create a sensor object, where this method can be found inside the documentation under robot. If you scroll all the way down, it'll be there. And then I pass the sensor name into it. Then I enable it with a time step, and then I can get value. And you can find all the information about get value inside documentation under the particular sensor that you are using. So now you should have a pretty decent idea about how to use motors and sensors in Webots. In fact, you could probably start writing a robot controller for this robot to navigate the maze and avoid these walls. Remember, if you have any questions about any of the Webots or Erebus topics, make sure you hop onto our live Q&A session on May 30th at 10 a.m., which is this Saturday. Another thing to note is these past few tutorials have been focused on just Webots in general, how to use motors in Webots, how to use sensors, how to work with the environment. But the next few tutorials are going to be focused on specific aspects of the Erebus competition, like victim retrieval and maze navigation. So just keep them in mind as we move forward. So that's about it for sensors in Webots. Have a great week, and we'll see you next time.